we discuss about different types of models and different types of membrane processes. I try to introduce the membrane processes for your family. In this section, we introduce all of membrane processes, and we'll first speak about the membrane configuration and the membrane models. Membranes can be fabricated as a flat sheet or as a tubular. Okay? We can prepare the membranes as a plate form or as a tubulars. If we reduce the tubular diameter to lower than millimeter size, we have hollow fibers. Hollow fibers is similar to the tubular membrane, but the diameter of these tubes is very small, and by this reducing the tubular diameter, we increase the surface area of the membranes in a specific volume. For flat sheet membranes, we have two modules. After preparation of the membranes for increasing the stability during the test and for increasing the surface to the volume, we change the membranes to the module. And in this slide, I want to introduce these modules. For flat sheet membranes, we have two modules. One is plate and frame, and another is spiral wound. For tubular membranes, we have also tubular modules that we have a big tube that can contain many number of the tubular modules together, or we can produce many tubes in one ceramic membrane. As shown in this slides, you see we have a structure that have many number of the plates. This is plate, these are plates, and this metal structure is frame. We say plate and frame. In a frame, in one frame, we have 20 plates. For fabrication of plate, we have this polymeric structure, you see, like as this. And in the left and the right side of the plate, we attach a membrane sheets with adhesive. You see, in the right, when we have this plate, in the right, left, and the left side, we have the membranes, and this membranes is immersed membrane, and for driving force, we used vacuum suction. In the next presentation, I say that we have direct pressure and vacuum pressure. In this style of modules, we have a suction pumps, and we have a vacuum pressure that apply for this tube. You see, this tube is connected to the big tube, and this tube connect a tube, permeate tubes connected to the vacuum pump. Therefore, as I said, in a vacuum, most applied pressure is 1 atmosphere. Therefore, this module is suitable for microfiltration and ultrafiltration. We have not reverse osmosis plate and frame modules. This is suitable and mostly used in membrane bioreactors. These frameworks used in membrane bioreactors for separation of microorganisms from activated sludge and increase of MLSS of the microorganism mass. Very good modules from fouling view because we can purge air or oxygen on the surface of these modules, and cleaning of these modules is very easy. With a sponge, we can clean these membranes for removal of the microorganisms and other dirt. But the surface area the volume is low because the flat sheet membranes is not a spiral, is not changed and directly used. The module preparation is simple, is suitable for MBR system, and the cleaning is easy. You see, this is immersed in the activated sludge for treatment of wastewater. There are different structures for plate and frame. Was designed is stacked plate and frame. As you see, for this one, you see this is a plate, this plate, and between two plates, we have a free space. Together, huh? And between the plates, you see the feet come and go from the plate. And this module is rotary. When we have this rotary during of this central pipe, this rotary causes the reducing of the fouling, like as aggregation, and this agitation reduces the fouling and low need to the cleaning of this membrane. You see, the feed comes and every passed permeate collected in this central tube. You see permeate, and after the finishing of this road, the concentrate goes out from the membrane modules. There are other designs that I have not time to discuss. Second module is tubular module. Tubular module, we say that diameter of more than 3 millimeters, or more than 3 millimeters, and mostly used in industrial microfiltration, can be fabricated from polymeric and can be fabricated from ceramic ones. You see this ceramic tubular modules. These tubular modules mostly used for separation of particles, and most used in clarification of fruit juice. For example, we have a pulp in orange juice, and we want to clarify the orange juice. In this case, we must separate this pulp from the orange juice or apple juice. And in this case, this module is used because the pulp is big, have a 2 millimeter, 3 millimeter in length or in diameter. We cannot use spiral wound. In spiral wound, the spacer between the membranes is very low. I showed the video. And when we have the pulps and particle, this particle can block the entrance to the module. Therefore, every place that we have a big particle, such as concentration of polymers. For example, in petrochemicals, one of the methods for production of PVC, polyvinyl chloride polymer, is suspended method. In suspended method, the PVC particle is produced, and for separation of the water from these suspended solids, use the tubular membrane. In the final lecture, I will speak about case studies. In this case, I more discussion. Generally, this tubular membrane is MF membranes. The cleaning is easy, this method, but the surface area is low, and the fouling can be controlled with increasing of the velocity and cross-flow speed. The third module, and the famous one, is spiral wound membrane modules, mostly used in NF, RO, gas separation, some MF, some UF. And for producing of this spiral wound, we use flat sheet membrane. With the wounding of a flat sheet membranes around a central tube, we change the flat sheet to a tubular modules. Okay, this is spiral modules with different diameter. Usually 8 inch, this is 8 inch, this is 4 inch. With the increasing of the diameter of the modules, the area of the membrane is increases. We have a central perforated tube that permeates, collect in the center of a tubes, you see. And between the membrane sheets, we have a feed spacer and permeate spacer. We want to have a distance for passing of permeate and feed from two sheets. Therefore, with using of the spacer, you see, this is a spacer, we distance between two sheets for easy passing of the feeds. We have videos, please play the video. In this video, we show that we how produce the spiral wound models from flat sheet membranes. We first prepare an envelope, and after round and wound about the tubes. Exit and play the videos. There are many videos in YouTube. This is pressure vessels
to treat wastewater after the ultrafiltration process.
And inside of this pressure vessels, we have a module. This is a prepared flat sheet membrane. For RO membrane, we have a 3-layer, non-woven layer, polysulfone layer, and polyamide layer. The thickness of polyamide is very low,
that removes nutrients,
200 nanometer.
and viruses
The
from
selective
water.
layer is polyamide. For modulation, we first
Membrane flat sheet
prepare an envelope, and this is a feed channel spacer
and creates space between the membrane sheets
for
the
passing
feed
of the
water.
feed.
A sheet of permeate
This
spacer
one is
added
the
to membrane
permeate
sheets
spacer.
and feed channel spacer.
Permeate spacer,
enables the
membrane,
final
feed
recycled
spacer,
water product,
membrane,
permeate,
permeate
to
spacer.
flow evenly across the
Series,
entire membrane surface, even under high pressure. The back of the
see,
membrane is completely sealed to the edges
we
of
use
the permeate
adhesive
spacer.
for
membrane sheets are
closing
glued along
all
each
of the
the three
membrane, and
exposed sides
open side
rolled
is
around the
connected
core
to
tube.
the central tube.
Feed water
When feed pass,
brain.
it
Water passes
penetrate,
through the membrane
permeate
surface
to
into
the entrance of envelope and
permeate.
the spiral wound and reach to the central
This water
tubes.
is the final product, or permeate. There are 7 spiral wound
You
elements
see,
loaded
in the
in one
pressure vessel, for
Once the
increasing
end adapter
of
is connected to the
recovery,
last element
I
and the
say
pressure vessel
each
is
module
sealed,
have
feed water
recovery
can
10
be
or
introduced.
15%.
Feed water is
For
pumped at high
increasing
pressure
of
into the
recovery
vessel.
in each
As it
pressure
travels,
vessel,
small
we have
molecules
4,
like water
5 or
pass through the
6
membrane,
modules.
while larger particles such as salt, bacteria and viruses do not. The final recycled water product is collected from the end of the elements. The concentrate or reject from that vessel flows to another stage, producing more recycled water.
We have a feed entrance divided to
At St.
2
Mary's, there are
streams,
6
one
reverse
permeate
osmosis
and
treatment
one
trains, each
concentrate.
with 3 stages.
You see
This
here
design produces
the membrane in 3 steps. I speak about the stage in the next slide. You see stage 1, stage 2, and stage 3. For increasing of the recovery, we can use in membranes in 2 or 3 parallel steps. That means, for example, the concentrate of stage 1 can go to as a feed in the second stage, or the permeate of stage 2 can be go as a feed of stage 3 for increasing water quality and recovery.
Through stage 3, where the last percent of all feed water is recovered as recycled water. An average of 50 million litres of recycled water is produced every day at St. Mary's. The remaining concentrate contains so much salt. This concentrate stream of 8 million litres a day is sent to North Head Wastewater Treatment Plant.
Play other video.
Released into the ocean.
Is finished. To hydronautics. This is similar to the first video. Hydronautics is a membrane production factory. This is also similar, show that how to repair the membrane model.
With a microporous polysulfone layer. This provides additional support for the top 0.2 micron thick membrane barrier layer. This top barrier layer makes the actual separation to purify the water.
This bright layer is the active layer, and another layer is only supporting.
American material, few thousand
Show the chemistry of the this layer. For fabrication of RO membranes, we use interfacial polymerization that I will discuss tomorrow about this. And when these monomers connect together, we have some pores. The water can easily pass from this pore, but the hydrated ions, sodium or chloride, cannot pass.
The combination of these 3 layers makes a durable membrane flat sheet that is used in each spiral wound element. The membrane flat sheet is then combined with a sheet of feed channel spacer. This provides turbulence and creates space between the membrane sheets to allow uniform flow of the water to the entire membrane.
All of permeate goes to the
membrane and feed channel
central
spacer
tube.
are then combined with a sheet of permeate spacer, which provides open flow channels for the
Usually for 8-inch modules, we have 24 envelopes.
Sleeves are glued along each of the 3 exposed sides. And then rolled around the core tube.
This is anti-telescope, and for pressure resistance, we have a fiberglass layer, about 3 millimeter, 4 millimeter of the fiberglass coating for pressure stability.
Clean water or permeate.
This is feed spacer,
membrane surface
and
into the permeate channel, and
between
then
the
flows
two
in a similar
membrane is
direction to the
permeate
center
space.
of the
This
element and is
anti-telescope.
collected into the core tube. Hydronautic spiral wound elements can then be loaded into pressure vessels.
Modules
interconnected
go
with
to the
additional elements to complete
pressure
a number of
vessels.
design specifications. Once the end adapter is connected to the last element and the pressure vessel is
Concentrate
feed water
of the first module go to the second module.
the feed water that does not permeate
And the permeate collect in the central tube. This is the permeate,
becomes enriched into
and this
salts as it
red
travels
is
through the
concentrate.
The permeate water then flows out the end of the vessel and is collected as the product. And the reject or concentrate from that vessel may then flow through another vessel producing more permeate. The remaining concentrate may then be disposed of as waste or partially recycled as the feed.
For brackish water, recovery is about 70 to 90%. And play the third video. Before modulation, we must, we must prepare the membranes, and we will discuss tomorrow. But I want to show that we first prepare these membranes, and next began to modulation. For reverse osmosis module fabrication, we need 14 instruments, 14 equipments that I showed in the slides. Therefore, the production of the spiral wound is expensive because we need many devices for production of different sections of the modules. This is a phase inversion method. You see, we have a polymeric solution like honey. You see, like it's honey, viscosity is similar to honey, and also the color. This is the film applicator. We can adjust with this the thickness of the layer, and the fabric began go from the bottom of this casting knife, doctor knife, and coat 200 or 150 micrometer of the polymer solution on the surface of the fabric, and directly go to the non-solvent. And when go to the non-solvent, the polymer, the liquid polymer solution changes to the solid one. And we say that phase inversion or phase separation occurred. Production of the membrane spiral wounds is high technology and need to control all of the process. The process is simple, but controlling the conditions is very hard. Measure the thickness of the membrane. Okay, I will tomorrow discuss about this fabrication. Go to slides. Okay. You see the production of this spiral wound, but we need many equipments for fabrication. When we speak about the spacer thickness, this usually is 750 micrometers. That means the feed channels have the height of this one. Therefore, I said that spiral wound is not suitable for particles separation because the pulp can be block the entrance of the feed to the spiral wound. Therefore, before spiral wound, we need to pre-treatment for removal of particles. Before the spiral wound modules, we need to separate particles, usually use cartridge filter for removal of a solid. Permeate spacer thickness, you see this amount, and total membrane thickness after the total thickness with non-woven polysulfone and polyimide layer is about 150 micrometer. Usually the non-woven thickness, this one, and the polysulfone thickness, this one. That sum of this is this number. For fabrication of spiral wound modules, we need 14 equipment. One device for production of central pipe. We have a injection molding device for production of the central pipe. After preparation of the central pipe, we need equipment for perforating and producing of the pores in this central pipe. We need a device for production of anti-telescope and production of the O-rings for black O-rings and other machines. Therefore, I want to say that the production of the membrane modules is very expensive. Therefore, the price of the 1RO modules with 8-inch is about $700. Need to gluing device, trimming device, and fiberglass coating. All of need expensive instruments. The fourth modules is hollow fiber. Hollow fiber membranes have ID less than 1.5 millimeter. I said that the tubular membrane have 3 millimeter, higher than 3 millimeter. Hollow fiber membrane is lower than 1.5. There is another categorization as capillary membrane. Capillary membrane between the hollow fiber membrane and tubular membrane, and the diameter is between 1.5 to 3 millimeter, but not usual. We have some capillary membrane, but not usual. Most of hollow fiber membranes have this diameter. You see that the human hand can be thousands of the hollow fibers. And the most properties of this hollow fiber membrane is that very high surface. And when we have a high surface, the productivity of the membrane will be increased. But one problem is that the stability of these fibers when fabricated from polymer is low. We cannot apply high pressure. In high pressure, these fibers can be tear and destroyed. Therefore, the surface area is high, but we cannot apply high pressure. Also, the washing and cleaning of the hollow fiber membranes is hard. In this slide, we compared the tubular, spiral wound, and hollow fiber modules together. A specific surface area, you see, meter square to meter cubic. Hollow fiber is very high surface area. You see, hollow fiber 15 times more than a spiral wound, and spiral wound 3 times more than the tubular. The surface area is high, but the flux of hollow fiber membranes is low. The flux is low because we cannot apply high pressure. We cannot, the surface area is high, but the flux is low. Therefore, when we introduce new concept, productivity, or production, that is the flux and surface area, we see that generally hollow fiber membranes have high productivity. But I say that hollow fiber membranes only used as a low pressure gas separation, microfiltration, and ultrafiltration membrane. Hollow fiber membranes cannot produce for RO. 50 years ago, some companies fabricated reverse osmosis hollow fiber membrane, produce hollow fiber membrane and coat polyamide layer on the polyamide, and fabricated a factory in Kuwait country. But after 2 years, all of the membranes destroyed and forced to change the hollow fiber RO membranes with spiral wound membranes. Therefore, in 15 years ago, hollow fiber RO membranes was fabricated, but because no stable, today not produced. When we check the cleaning, I say that the tubular membranes very easily cleaning and very easily replacement and no plugging, very small plugging. But hollow fiber membranes have a very high plugging, replacement is impossible, and the cleaning is very hard. We write not possible, possible. In some cases possible, in some cases not possible. But generally, the cleaning of the hollow fiber membranes is very hard. Therefore, as a conclusion, when we have a low pressure, low flux, the hollow fiber modules is the best choice. But for high pressure, we use spiral wound modules. And when we have particles in the feed, we try to use tubular membranes. As we show in the video, we have a different configuration and staging in the use of the modules and pressure vessels. In the first design, we have 3 parallel module or pressure vessel, and if a module have independent behavior, independent product, and in the final, for example, concentrate of all 3 mixed together and the produced water mixed together. And we have one stage. We have different modules, but all have a similar fit and have a similar permeate and concentrate. Okay? With this, the parallel. But in the second configuration, for increasing of the recovery, I said that we have a usual recovery of 60, 70 in reverse osmosis. For increasing of recovery, we can the first step, concentration, go as a feed step in the second. When we see water or feed enter and divide to 2 streams. One stream is permeate, and independent. But the second stream that is concentrated, our brine, for more recovery, go to the second step. And also the second step concentration, go to the third step. This is the series membrane. And this is for increasing recovery. For example, in this case, we have a brackish water modules. In this case, we can see water modules. And in this we can membrane distillation modules. The membranes types can be changed. But we want to increase the productivity and recovery. And in this case, we will have very concentrated solutes with high concentration of salts, and we must treat this brine for separation of salt. Usually, sedimentation is used for this purpose. In this second design, that named as Christmas tree, you see we can use both the permeate and brine of the first step go to the second step. When we use the brine, we use the permeate for second steps, the aim is increase of the purity. I show here. When we have a membrane, permeate, go to the second step, permeate, not concentrate. The aim is the high pure water. High pure water. For example, here we have this. When we go to the here we have this ppm, but we need this one. When we go the permeate of the first step to the second step, the aim is production of the high pure and low solid. But in this case, when we go the concentrate to the second step, the quality of the product water is similar, no change. But the recovery increases. In this case, the aim is increase of recovery. In this case, we want to increase the purity of the product. In the Christmas tree, we want to both them, both increase the recovery and both increase the purity. There are many different staging and configuration. Every company that fabricates the modules, such as hydronautics, such as FilmTech, have their software. And in software, you can select different design, different modules, and have 5 steps. And in step to step, you design, and based on your water quality and the concentration of feed, you can reach to different recovery. And if your design is not true, your data is not true, you cannot go to the second or third step. In software, you must type and insert true data. If your data have a wrong, the software can predict and go that, for example, the concentration of anions and cations is not equal. We know that the charge of the solution is neutralized. When we have 10 cations, we must have 10 anions. We measure the feed concentration, And if the concentration of anions and cations is not equal, the software is not accepted and say that your measurement is not true, and others. The software is very good for this staging and configuration. Is there any question about module? If need, I can more discuss. This is tutorial, and in tutorial we must discuss if you want. No question? Oh, okay. I go to second step. In the second step, I want to introduce the membrane processes. As we have 22 membrane process, and we have more than that, maybe 30. But this process is relatively famous. The first processes is the many famous microfiltration, ultrafiltration, nanofiltration, and the reverse osmosis. And the first lecture I discussed about that the separation is based on the pore size, and the MF have the big size, and the NF have the low pore size. This is a typical large-scale MF, UF, and NF or RO plant. We have a feed tank, usually. We have many pumps based on the volume of the factory, that these pumps apply pressure to the feed, and feed go to the pressure vessels and pass from the modules, divide to stream, one concentrate and one permeate. Based on the process, concentrate can be product or permeate can be product. In UF, usually concentrate is product. For fouling reduction and control of conditions, usually we add additive to the feed. You see a little tank with a little small pump that dosing some additives to the entrance of pumps. These additives reduce the membrane fouling. Mostly is the pH adjustment. We control of pH, we can reduce the fouling. We can change the protein charge, membrane charge, or we can change the sedimentation of the salts on the RO. Or we can use anti-escalant. Anti-escalant usually insert to the RO feed for reducing the sedimentation of the saturated salts, and other. Many additives can be used. And go to the modules and divide into stream. This is a usual UF, NF, and MF process. About the control process of this unit, so we see that we have a pump, we have a pressure indicator transmitter before and after membranes. We must apply delta P as a driving force, and we must measure all of the parameters. We measure the pressure, flow, and temperature for controlling of the conditions. For applying the pressure and controlling of the recovery, we have a closed loop that measures the flow and control this valve for controlling of the recovery and pressure. With closing of this valve, we reduce the flux and increase the pressure. This is a typical control system. You see microfiltration and ultrafiltration in dairy industry. In dairy industry, microfiltration used for separation of skim from the milk and sterilization of the milk. Microfiltration can be separate the bacteria from the milk. You see that all of the pump, this is pump, and this is pressure vessel, all of the tubes is stainless steel. Because for sterilization, every day use the chlorine agent and the oxidation agent for disinfection, and all of the systems should be resistant to oxidation, and therefore not use plastic or metal, simple metal. Therefore, this dairy industry need very high capital cost because this pump is very, very expensive. About the application of UF membranes, UF membranes have the most application from different fields. For example, oil-water separation. With UF, we can separate oil from water or water from oil. If we have a hydrophilic membranes, we can separate water from oil. And if we have hydrophobic, we can separate oil from water based on the concentration of oil and water. Separation of whey, you know whey is the product of cheese. After producing of cheese, we have a liquid that have a soluble proteins. For separation of soluble proteins, we can use the UF membranes, and we have a UF cheese. We have a UF cheese. The name of the cheese is the UF cheese. That means UF used for the concentration of this cheese. Concentration of biological macromolecules, such as membrane bioreactor. We separate microorganisms from the sludge. For recovery of the paint from electrocoating, concentration of heat-sensitive proteins. We can, you know that the proteins, when heat, denaturalization. The proteins is denaturalized. And the denaturalization changes the properties of protein. Therefore, when we use the membrane, in membrane separation, we do not need heat. And therefore, the proteins is safely separated. Concentration of gelatin, in production of gelatin, we must separate the water. As you see, in most cases, we want to separate water from a solution. And the product is concentrated, not water. In the gelatin, our product is gelatin concentrated solution, not gelatin water. Separation of enzymes. Enzymes is a protein. Pulp mill. In the pulp mill, we use the tubular membrane and other processes. There are many, many applications for UF membrane. Another application is gas separation. In gas separation is a high technology with the polymeric or ceramic membranes. We can separate two similar gas. For example, nitrogen and oxygen have a similar size, but we can separate them from together by membranes. In lecture 9, I will speak about gas separation. Therefore, I pass this slide. This is a commercial hollow fiber gas separation membranes that I opened this. This is used for hydrogen separation. This is hydrogen separation. hollow fiber membranes. One of problem of gas separation membrane is aging. In aging, the polymer from flexible state changes to the brittle state. When I contact with these hollow fibers, the membranes is powdered, very, very brittle, and cannot touch this membrane and destroy the membrane. Very, very application I will discuss in lecture 9. Other application is a membrane bioreactor. In the membrane bioreactor, you now, in biological reactors, the microorganism eat the carbon-based material as a feed and destroy the organic matter. Microorganisms with eating of the chemical oxygen demand, COD, remove the COD and BOD. And after this treatment of microorganisms eat this food, and the population is increased. And we must separate the extra microorganisms. The traditional method is use of the precipitation tank or sedimentation tank. And because the hydrophilic nature of microorganisms, the sedimentation is very slow and therefore need a very big tank for sedimentation. And almost 1/3 of the treatment plants is related to the sedimentation of the microorganisms. But when we use the membranes for separation of microorganisms, we no need to the sedimentation tank, and the size of the treatment unit is mostly reduces, and the quality of the water is also high. In sedimentation tank, we have not complete and good separation, but in membrane bioreactor, membrane can be separate efficiently the microorganisms. This is an experimental setup in lab scale that used hollow fiber membranes for separation of the microorganisms. Any question about discuss? Huh? No discuss. Huh? Please discuss. Another membrane process is pervaporation. Pervaporation. Pervaporation is used for separation of the liquid. For separation of low amounts of impurity from the solvent. The famous example is the separation of water from ethanol. The famous example I show this, you see, you know, after biological change of the sugar to the ethanol, by distillation, we can separate ethanol from water. And when we boiling the mixture of ethanol and water, ethanol have low boiling point and vaporize and go to the gas phase. And with condensation, we can separate alcohol or ethanol from water. But in this point, in this percent, 96% of the alcohol and 4% of the water, we reach to the azeotrope point. In azeotrope point, the difference boiling point between water and alcohol is removed. And when we boil this solution, the composition of the alcohol water in gas is similar to the liquid phase, and we cannot separate 4% of water from ethanol. For resolving this problem in industry 30 years ago, add benzene or toluene to this 96% and redistillation. By addition of benzene or toluene, the azeotrope destroyed, and with redistillation, the absolute ethanol, 100% ethanol is produced. That is very expensive. If you want to buy 1 liter of 96 ethanol, it's maybe 50 rupiah. But if you want 1 liter of absolute ethanol, it's 500 rupiah. 10 times is expensive because the separation of this 4% is very important. And in many organic reactions in the petrochemicals, we need a pure ethanol. The water is poison, is toxic for the reaction. For separation of this 4%, the famous technology now in the world is using of the pervaporation membrane. In pervaporation membrane, we have a non-porous membrane. Here we have no porous. Membrane is dense. We have a feed, and here is the air. But for increasing driving force, we have here vacuum. We have a little vacuum that causes the driving force for penetrating and permeation of the ethanol from this membrane. Therefore, in PV process, we separate mixture of liquid. The membrane is non-porous, and membrane can be both hydrophilic or hydrophobic. If we want separate water from solvent, for example, we have a hexane and have a 1% water. We want to remove 1% water from hexane. We used hydrophilic membranes that water pass and hexane do not pass because hexane is organic. But reverse, if we have a 1% hexane in 90% water, we use hydrophobic PV membrane that hexane pass and water not pass. Therefore, in PV, based on the separation molecule, we can use hydrophilic or hydrophobic membrane. Usually, the vapor can permeate. Liquid, some ethanol or hexane also can diffuse. But we know the diffusion rate of gases is very high than liquid. Therefore, for helping to increasing diffusion coefficient, we heat the feed. But this heating is not very high. For ethanol water in azeotropic, we heat about 50, 60 centigrade, not reaching to boiling. We want to reduce the energy consumption. With increasing of the heat, mostly 50, ethanol, some of ethanol can change to the vapor, and the vapor pass from the membrane. And this pervaporation, permeation vapor, is produced from mixing of permeability and vaporization, pervaporation. Therefore, the vapor can pass from the non-porous membrane. Here is the partially vacuum, the vacuum level. And after reaching of the vapor here, we need to condensation. For condensation, we condense and reduce the temperature for changing of the gas to liquid. Therefore, you see in the permeate, we have a condensate. This is heater, this is refrigerator. Reduce the temperature. This is a schematic of the pervaporation membrane. The mechanism of separation is solution diffusion because we have not pores. The membrane is non-porous. The ethanol adsorb on the PV membrane and diffuse. There are many applications. Removal of water from organic solvent, dewatering process is dehydration or dewatering, separation of the ethanol, alcohol from fermentation baths for ethanol, propanol, and very, very different. And there are many factories that produce the pervaporation modules, but pervaporation modules is expensive relatively, 6 times of the RO membranes, half price. You see, the pervaporation membranes can separate isomers from together. Isomers, cis trans, have the similar molecular weight, and separation of them with UF and F is not possible. But with pervaporation, we can separate isomers from together. But you know the Brazil is the most producing ethanol in the world. And in Brazil, most of cars use ethanol instead of benzene, or mix of benzene with ethanol. You can use 50 ethanol and 50 benzene or diesel in your car. And in the Brazil, the first plant of pervaporation about 50 years ago is constructed. This is a Sulzer company. Sulzer is the famous production of PV modules, and that this design is hybrid system that for ethanol or isopropanol separation. This percent produced by distillation, and for complete removal, usually used the pervaporation process. The membrane is located here. Any question about PV?
Organic
No, this is have some. Repeat.
Yeah. Are you able to hear? Yeah. I mean, like, we generally use dimethyl formamide for the synthesis of MOF. Yeah. Generally, we, face the problem of separating this DMF from some organic substrate that we, like if it is in the DMF solvent, we can't separate the DMF because of its high temperature.
Yes.
And also we face the problem of DMF and water. We can't separate that because it will form azeotrope at 100 degrees Celsius itself, where water has to evaporate. So we can't do through normal distillation process. Is that possible with your membrane technology, the DMF separation?
You want to remove DMF or water?
DMF and waters, we want to separate DMF itself because of its high temperature.
How many DMF? The amount of DMF, how many? 10%, 5%?
So generally, like I encounter 5% of DMF. 95%.
You want to separate DMF from your water?
Yes.
In lab scale?
Yes.
In lab scale, you need, you cannot use PV, so you need the heater, you need the vacuum pump and condensation, and you must buy the PV. But the DMF boiling point
153 degrees Celsius. 153 degrees Celsius.
Yes, but the water is 100.
Yeah, but it will not be possible. I tried through that
you cannot separate them.
Yes, sir.
You can use zeolites. You can hydrophobic zeolites can absorb the DMF, can absorb DMF or organic pollutant from water. When you can use you prepare a hydrophobic zeolite column and pass your solution, and the DMF can absorb on the zeolite and water pass. And can you reduce the DMF? You can ask from organic chemistry students. Mostly they remove the organic from the water for impurification of our products.
Okay.
You can use zeolite. But PV is, can you use PV in industry, but in lab scale, it's very expensive for you. When we want to use hydrophilic polymers for PV, we usually use polyvinyl alcohol. Polyvinyl alcohol is a hydrophilic per evaporation polymer, and for reducing of the swelling, usually cross-link the PVA for separation of water. For separation of DMF, you must use PVDF or PTFE membranes, non-porous membranes, for separation. The other process is dialysis. In the MF, UF, NF, RO, most of gas separation and pervaporation, the driving force was pressure difference, delta P. In dialysis membrane, the driving force is concentration difference, delta C. Here, we have a delta C. This membrane, similar the ultrafiltration membrane. We can use ultrafiltration membrane as a dialysis membrane, similar pores. But in UF, we apply pressure for feed side, but in this dialysis, we have not pressure. The pressure of the feed and permeate side is similar, okay? No pressure. But we have a difference in concentration, and we have a difference in size of the molecules, okay? You see here, for example, we have a pore size. Usually this pore size for dialysis membrane is 20 nanometer. In 20 nanometer, you see that the big molecules cannot pass. If we apply pressure, also they cannot pass. But we want to separate a selective molecules from the feed. You see here, this blue with thick sign have not passed. The size cannot be from the size, but they cannot pass. Why? Because we have these molecules in permeate site. In the MFUF, in the permeate size, we have only air, weather, no solution. But in dialysis, in the permeate size, we have a flow of permeate. We have a receiver liquid. In the both side, feed side and permeate side, we have a fluid. This feed flow, and this is the receiver or dialysate. When we have these molecules or ions in the permeate size, we have not delta C, because the concentration of this blue is similar to the permeate site. Therefore, these blue ones do not permeate. But in this red, we have not here the red ones, and we have a delta C, and those can pass from the membranes. Therefore, in dialysis membranes, we have two mechanisms. For size effect, big molecules cannot pass. The small ones, if we have a different concentration driving force, it will be passed. If we have not, they cannot pass. The most and famous application of the dialysis is hemodialysis, that act as a kidney for separation of impurity of the blood and the urea, lysozyme, and other dangerous molecules from the water can be separated. But we do not sugar of the blood separate, okay? If the sugar of the blood is reduced, we have a healthy problematic. Therefore, we add sugar, this is sugar. And the sugar of the blood cannot pass because no difference in sugar concentration or NaCl. We know the blood is salty. We use the salty solution, and the salt of the blood no pass, but the urea can pass and separate from the blood. Also, there is the other application, for example, recovery of sodium hydroxide or recovery of the expensive metals, such as gold from the streams. We can use this hemodialysis or dialysis process. The membranes in dialysis is porous. The size is similar to the UF membrane, usually fabricated from polyethyl sulfone, polysulfone, and others. This is the models of the dialysis and hemodialysis. And most of hemodialysis membranes is hollow fiber, because we want to increase the surface and reduce the time of hemodialysis. The hemodialysis when we illness, the hemodialysis illness is need 2 times in a week go to the hospital and hemodialysis for 2 hours. If we use the flat sheet membranes instead of hollow fiber membranes, the time of hemodialysis increased from 2 hours to 6 hours. Therefore, with use of hollow fiber modules, we reduce the hemodialysis time. Any question about dialysis? A relatively new membrane process is imprinted membranes. Imprinted membranes show in this slide. From the first time, we want, and we know that we want to prepare a membrane for separation of a specific ions or a specific molecules. Okay? This shows that when we, from the first time, we prepare an imprint only for this molecule, and other molecules cannot pass from the membrane. Therefore, we say imprinted membrane. For example, show that after preparation of these membranes pores suitable for this key, not for this one. Therefore, these membranes act very, very sensitive and prepared from polymers. And these polymers mostly used in sensors for detection of some impurities in the water. It's very, very sensitive. And we can use these polymers for the fabrication of imprinted membranes. Based on the application, this imprinted membrane can be categorized to ion imprinted and molecular imprinted. Membranes, that means ion imprinted separate a specific ion, such as nickel, cobalt, heavy metals, and the molecular separate organic matters from water. For preparation of this ion imprinted or molecular imprinted membranes, if we have a template molecule, we want to pass only this molecule from the membrane. Therefore, we prepare a specific site that only match with this molecule. And other molecule cannot absorb in this free location and cannot pass. Okay? Mostly can be used as an adsorption membrane. Mostly can absorb a specific metal such as gold, silver, palladium, platinum. And after adsorption, we can separate the membrane and go to the release solution. And with change of pH, usually these adsorbed molecules can be desorbed, and we can separate the specific molecules. For preparation of this structure, we must use network polymers. Network polymers, that means between the chain of polymers, we must cross-link. Because with the change of temperature, the imprint should be stable. And for stable configuration, we used 3D dimensional polymers. Therefore, we have a monomer, target, and we have a cross-linker. We mix monomer, cross-linker, solvent, and target together and prepare a film. And after film, we go to the membranes, to the oven, and with heating or UV irradiation, complete the polymerization, and the obtained films can act as a membrane. This is high technology membranes. This shows that we can use one monomers, two monomers, or three monomers. But necessary we have a crosslinker. Crosslinker have two functional group for polymerization that connect the top chain to the bottom chain, and we have a restrict and very hard network. And the obtained pores is special for this molecule. For example, with this method, we can separate trans from cis. Per evaporation also can separate, and imprinted membrane. In per evaporation, for separation of two isomers from together, we must have difference in boiling point in per evaporation. Because we must have a difference in boiling point, one isomer change to the vapor and pass the membrane. But in this membranes, we no need to the difference in boiling point, and the membrane's free space is based on the difference in structure. This membrane is suitable for this one and not suitable for this one. And we can separate two isomers or enantiomers from together. Any question about imprinted membrane?
So previously you mentioned about the isomer separation with respect to per evaporation. Their boiling point difference is required.
In per evaporation, we need the difference in boiling point between two isomers. But it's no need. Separation based on structure. Another process of membrane is electrodialysis. In electrodialysis, we use both cation exchange membrane and anion exchange membrane in parallel. Okay? We have one anion cation, anion cation, anion cation. Okay? And we want to separate salts and charged molecules from together. And the driving force is delta E, electrical charge. Therefore, we have an anode and cathode. Okay? And between this anode and cathode, we have usually 10 membranes. 5 is cation and 5 is anion. Anion, cation, anion, cation. And the distance between two membranes is about 1 millimeter. When you see electrodialysis, you see only two electrodes, two metals, with very compact. But in this area, in this 2 centimeters, we have 10 membranes, and distance between the membranes is 1 millimeter. Why is near? Because we reduce the electrical resistance. We reduce the ohm. And as you see, in anion membrane, only pass the anion. Anion membrane pass anion, cation membrane pass cation. Okay? This is a sodium exchange membrane. This is a color exchange membrane. As you see, with, we have a one feed and this 1 feet enter between all of the membranes, but the product is divided to stream, concentrate, and diluted. You see here, color go to the right, sodium go to the left. And here we have a purified water or desalinated water. But in the right or in the left of this area, we have a concentrated, because the color cannot pass from the cation and the sodium cannot pass from the anion exchange membrane. Oh. And the driving force, you see, the sodium wants to go to the left because the negative charge here, all of the cations go to the left, and all of the anions go to the right because they're positive. But therefore, we have a one rod with concentrate, and one rod have a desalinated. Driving force is the electrical, and it is similar to that. For this exchange, we need some functional groups in the membrane body. For sodium passaging, we need sulfonation group, sulfonation negative group, absorb the sodium. And for color passing, we need the ammonium positive groups on the membrane. Electrodialysis is good for low desalination processes, usually used after RO. RO reduce the high concentration to low concentration, and for low concentration use, we can use this for produce low saline. And we cannot produce demineralized water, DI water, because for conductivity, we need the ions. We cannot complete removal of the salts, because for conductivity between cathode and anode, we need to the ions. Okay? Usually this process now used in desalination of protein solution, in the fabrication of the in the fabrication of different type of protein lysozyme. For desalination of the protein solution, usually use the electrodialysis, very low use in the water treatment and reducing the salts. If used for groundwater, is used for brackish water, not seawater. This is the I discussed. This is the experimental device for testing of the electrodialysis membrane of ion exchange membranes. All is non-porous membrane, like as this. The Nafion membranes, Phelemion, Aquavion, all of these similar membranes and not porous. This is the industrial units of the EDR. Another application of membranes and exchange membranes is in the fuel cell that Professor Rocca discussed and will also discuss. We use the protein exchange membrane in the fuel cell for passing of the proton and going to the react with oxygen for production of H2O. Also, exchange membranes is used in color alkali industries. in chlor-alkali industries, we want to pass sodium from this anode house to the cathode house for production of the chlorine gas and hydrogen gas and hydroxyl solution that usually use the exchange membrane, sodium exchange membrane. Before membranes, usually use the diaphragm separator, and before the diaphragm separator, usually use the mercury method. The mercury method is very dangerous, and today use the membranes, such as this, for the production of the color gas, hydrogen gas, and hydroxide from NaCl solution. In this industry, saturated brine, NaCl solution come and electrolyze to chlorine, hydrogen gas, and hydroxyl for production of NaOH as an alkali. Another question? No question about exchange membrane. Liquid membrane also is used mostly for recovery of expensive metals. Liquid membranes similar to the liquid extraction. In liquid extraction, we have a ligand that's a specific complex with a metals and transfer that metal from water phase to organic phase. And in this membranes, we have usually carrier agent for separation. Have two types, mostly emulsion liquid membrane and supported liquid membrane. In supported liquid membrane, we usually have a ceramic membrane with big pore size that the pores of the ceramic membranes filled with the liquid. This liquid usually is oil-based, usually is paraffin that have a complex agent and can absorb from the feed water to the receiving phase. We have a source phase or feed phase, and some molecules can contact to the carrier and go to the receiving phase. And in this case, we can have passive or active transport. In passive, we say high energy, high potential, go to the low potential. But in some cases, we have an active transport, as discussed in the lecture 1. This is show also the different cells of the liquid membranes. You see in this case that we have a U tube. In the bottom, we have usually water. This is the water phase. And this phase is organic phase. Organic, usually on top of the water. And we have a micelles, our acceptor phase. These micelles can selectively absorb selected molecules from the organic phase to water phase or reverse, from water phase to liquid phase. Have different configuration for the cells for separation of these molecules. Usually we have a feed and receiver phase, and mostly used for recovery of expensive metals. Another membrane process is membrane distillation, or MD. MD is used for desalination, most application for desalination, and usually used after RO for treatment of concentration of RO. RO, when the concentration of the salt go very high, when reach the concentration to 100,000 ppm, in this concentration, RO cannot work because the osmotic pressure is very high, and this concentration caused to the saturation of many compounds, and this saturation can deposit on the membrane surface and cause to the fouling and scaling. I will next discuss. Calcium carbonate, calcium sulfate can be deposited in this concentration, and the membrane will be destroyed. In this case, we can use membrane distillation for more treatment of the saline solution, because in this case, we have no many concentration, and we have no pressure, delta P, because in this membrane type, the driving force is temperature difference. We have a porous membrane, and we want that vapor pass, not liquid. We want to vapor pass, such as pervaporation. We want vapor pass from the porous membrane. In the pervaporation, we have non-porous. In the MD, we have porous membrane. Both PV and MD, vapor will pass. We want only vapor pass, not liquid pass. Therefore, the membranes should be super hydrophobic. The contact angle should be higher than 120. Because when the water enter to the pores will be blocked, and the membrane do not work. The pores should be free, should be open for passing of the vapor. Therefore, water should not pass from the pores of MD membrane. Therefore, in this case, we use hydrophobic materials such as PTFE, PVDF, polypropylene, and other hydrophobic polymers, such polyimides also used, such polyether ether ketone can be used, and others. Therefore, in this membrane type, the driving force is delta T. We heat the feed. In this process, we heat the water solution, usually 80 centigrade, but we do not reach to the boiling point. And as I said, the most energy used in the phase change. When we have a boiling, in the boiling point, we need many energy. But we do not reach to the boiling point. We increase temperature to 70, 80, and in 80 centigrades, some vapor is produced and pass from the membrane, hydrophobic porous membrane, and condense in the permeate size. based on condensation method, in the permeate size, we have different types of MD. We have a direct contact membrane distillation. In the direct contact, we have a cold stream on the permeate side, okay, such as dialysis. In dialysis, we have a flow in the permeate side. In MD, we also have a flow in the permeate side. In the direct contact, the cold stream directly contact on the membrane bottom layer. In the first configuration, and this method is not good because the permeate solution, such as fit solution, can wet the membrane and fill the pores. Okay, we do not like the pores fill with the water. In direct contact, we have a second stream that the possibility of the going to the membrane pores is increased. In the second category, we have a vacuum. We have a not stream in the permeate side, and every permeated vapor sucked to the condenser and changed to the liquid. Therefore, in this area, we have a vacuum on the permeate side, but this vacuum should be very low. We do not like have a delta P. Okay, do not like. Therefore, we have a very, very low vacuum only for suction of the vapor. In the second design, in the third design, we have an air gap between the cold stream and the bottom of membrane. In the permeate side, we have an air gap that here we have a stainless steel metal. In the behind of the stainless steel metal, we have a cold water. Cold water reduces the temperature of the metal, and when vapor penetrates, diffuse from the membrane and go to the air gap area, when contact with the metal, condense and drops began to dropping. Okay? In this case, this space about 3 millimeter, 4 millimeter, and we have a metal barrier, stainless steel barrier, and we have a stream behind of this metal. In the last design, we have a sweeping gas. In this vacuum, we have a vacuum pump, but in this case, we have a sweeping gas, usually air or nitrogen, with low flow come from the bottom side, permeate side, and sweep every penetrated vapor, go to the condenser for condensation. The MD membranes can be flat sheet, can be hollow fiber, or can be spiral wound. We have a different module for these membranes. I discussed these slides. This is the lab scale vacuum membrane distillation. I say that we do not like the pores is filled with the liquid, and the pore size and the hydrophobicity of the membrane is very important. Usually 30 nanometer pore size is good, and superhydrophobic membranes, rough membranes, the surface roughness is very important. When we have a roughness membrane, the contact angle increases. Sweeping, we have a air or nitrogen sweep on the behind of the membrane. Any question about MD? No question? I will finish in 10 minutes. Okay. Other membrane process is membrane contactor. Membrane contactor can be used for degassing or gasification, like as at absorption column and desorption column. In, for example, natural gas have carbon dioxide and H2S, and these gases cause to the corrosion in the transferring tubes. Therefore, the natural gas companies separate the carbon dioxide and H2S from the methane with absorption column, that we have a amine solution that can absorb acidic gas. H2S and carbon dioxide is acidic gas, and amine is basic and can absorb this acidic gas. But in this case, we have a direct contact. And I said that the membrane process is indirect. In this process, the loss of the amine solution is very low, and the contact of between gas as liquid increases. In the absorption column, we have a tray for increasing of the contact between gas and liquid for mass transfer. In this membrane contactor, we usually use hollow fiber membranes, and hollow fiber membranes have a very high surface and increase the contact between gas and the liquid. Yes, in the fit site, for example, in the out of the hollow fibers, we have amine solutions, and in the inside of the hollow fibers, we have a methane and carbon dioxide. And carbon dioxide can penetrate to the amine solutions and separate. Therefore, in a membrane contactor, we use hollow fiber for increasing contact area. We use porous membrane, and we use hydrophobic membranes. Because in hydrophobic, the water cannot penetrate to the pores. Okay? The membrane contactor membranes is similar to the membrane distillation. Membrane distillation and membrane contactor have similar membranes. And the final process is photocatalytic membrane reactors, that PMRs. PMRs is similar to the MBRs, membrane bioreactor. In membrane bioreactor, we mix biological treatment with membrane separation. In this case, we mix photocatalytic activity with membranes. Photocatalytic activity with membrane. Photocatalysts degrade the pollutants, organic pollutants, with using of catalyst and photon. Photon can be produced from UV lamp or solar or visible light, okay? When the photon conduct to the catalyst surface, produce radicals, mostly hydroxyl radicals, and these hydroxyl radicals can degrade the organic pollutant. Usually membrane is used for separation of catalyst after photocatalytic activity, okay? Usually membrane act as a separator of the catalyst from the slurry solution. And in some cases, we can deposit catalyst on the surface of a membrane. But this is the most used. We have a external membrane that you see the light goes to the production of the radicals on the catalyst. And after the photocatalytic is completed, for separation of the catalyst, we can use the membranes. These membranes can be external or can be immersed in the feed solution, such as this. This is an external and can be used immersed. And in immersed, we use the vacuum suction for separation. Mostly MF and UF membrane is used for separation of catalyst. And in some cases, we can immobilize photocatalyst in membrane surface, but with immobilization, the surface area of the catalyst is reduced and the efficiency of the process is reduced. Thank you. In the last speech, everybody is tired and sleepy.
So all the participants are requested to make use of this opportunity to interact.
I try to, in this section, introduce only the membranes, processes, and have more time for more discussion. I will try to discuss about this mechanism in the next lecture, but if you want more explanation, we can discuss face-to-face.
Yes. So apart from the topics also that we are discussing here in this topic, in case you have any question from another or related topic, you can personally approach us or use this opportunity to ask this question. So I encourage all of you to, because these offline seminars are attended or organized because of that, to enhance the connectivity between all of you with the expert lectures. So if we do not ask questions now, if we keep silent, so we are losing out. So please understand that and feel free to ask anything. So that is my suggestion to all of you in order to enhance the objectivity or successfulness of this course.
We can discuss about everything, not memory. We can transfer our experience in water treatment and gas separation to you. If you have questions that not related to membranes, but if your mind, you can ask.
Yes, yes. That will be great. Yes.
So we are talking about liquid membranes.
Yes?
So commercially, are we using it?
Huh?
Anywhere liquid membranes? Because solid, that is well versed. But what about liquid membranes? How far is it?
You ask about application, huh?
Yes. Is it currently?
The application of the liquid membranes have some problems. The main problems is that the organic liquid that filled in the membrane matrix is not stable. After 1 month, littered to the feed, and after 1 month, we see that all of organic is finished. And this is the one problems in liquid, and therefore liquid membranes should be used in 2-3 days. And there are some plants in gold extraction that use this liquid extraction on the membrane surface for continuous separation. In the emulsion liquid membrane, the difference from the liquid extraction that our extraction is continuous. We have some plants that use the mixture of two organic phase and water phase, and after 10 minutes, let me to separate two phase and separate with the Buchner funnels. But in liquid membrane, we have a continuous extraction. But another problem that some this liquid when go to the water phase have some dangerous environmental, because most of this extractant is toxic, and generally the environmental problems do not permit to more development of this process. But in the gold process, now the extraction and production use cyanides. And cyanides is very dangerous. And in this case, use of the liquid membranes from environmental view is suitable and used for extraction.
One more question regarding this gas separation. Whatever molecules you want to separate, they have similar molecular weight. So if I want to separate one molecule, so what about the selectivity? So generally, reduce the selectivity. For example, similar molecular weight of like oxygen or nitrogen. These molecules, when you want to separate one molecule, other molecule also comes together. So which type of membrane separation this can be achieved?
Yes. In the gas separation, we have two kinds of membrane, porous and non-porous. Porous membranes is used in gas separation when the molecular size is very different. For example, separation of hydrogen from butan, pentan, very big pentan, hydrogen is little, and we can use porous membranes with mechanism of Knudsen diffusion for separation of this. But in the similar molecular weight, we have a solution diffusion mechanism and non-porous. In this case, we have two parameters, solubility and diffusivity. When we have a similar molecular size, the diffusivity is similar, but the solubility will be different. Based on the chemical structure of gas and chemical structure of the polymer, the solubility is different. One gas more soluble and other low soluble. Therefore, we have a difference in solubility. After solution, the diffusivity is no change. Therefore, in this case, we say this membrane and this gas separation is based on the solubility, not diffusivity. I will discuss about gas separation.
Thank you so much. Thank you all for joining in today's session. And we are very happy that we could organize today's lecture, and that Professor Gatanpur has enlightened us with so many information about this specific topic. And so tomorrow our session will start again at 10 a.m. as per schedule that we have shared with all of you. So please join us tomorrow here in this conference. Thank you for joining us today. Have a good day.
Thank you. Have a good day.